Here I want to talk about some of the basics of matrices and definitions. So these are key things that you need to know before you start to delve deep into operations we can do with matrices and some of the work that we're going to look at as we progress through this topic. So this video is really about rounding up some of these basics and talking to you about some of the laws associated with the basic operations we're going to be looking at. So first thing I want to tell you about is what a matrix actually is. So a matrix is a table or an array of numbers. Each of these numbers is referred to as an element or an entry, and they're arranged in rows and columns. We can define something called the order of a matrix, and this is given by stating its dimensions. So the number of rows times the number of columns. So for example, if I look at this matrix here, A, I know I've got 2 rows and I've got 3 columns. So this is a 2 by 3 matrix because I've got number of rows 2 by the number of columns, which is 3. So we can state the order of a matrix looking at its size dependent upon the number of rows and number of columns we have. Now the element of the matrix A in the ith row in the jth column, that's denoted by Aij. So if I was to look at this one here, this element here, the 4, that is in the first row and the second column. So what I'd be able to say is that A12, the first row, second column, that's equal to 4. If I look at this one here, well, that's in the second row and the third column. So I'd say that A23 is equal to 2. So we can denote each element on its own and essentially give it a name if you like, which depends again on the row and the column where it's situated. And matrices are categorized and named according to their shape. So we can have various shapes. Now I've got a 2 by 3 there, I can have a 1 by 2, I can have a 3 by 1. It all depends on the amount of elements that are in it, and we can categorize the matrices according to these. Second set of rules I want to talk to you about involves operations with matrices. Now, what they can be used for is one of the key things we need to think about. Now, they can be used to categorize data as long as we remember what each of the entries corresponds to. Now, let's imagine that we look at an example where what we do is we take, let's say, a spreadsheet that a booking clerk enters for the number of adults and number of children for, let's say, 3 cinema shows. So let's imagine I've got a spreadsheet there. I've got 3 cinema showings, so let's say A, B and C. And let's imagine that my rows represent the number of adults and the number of children. So let's say for showing A, I've got 2 and 3. For showing B, I've got 1 adult and 5 children. And for showing C, I've got 3 adults and 1 child. What I can do is represent this data here as a matrix, 2, 1, 3, 3, 5, 1. Showing each of those elements. Now all I have to do is remember what each row and each column represents. So for this one, as long as I remember the top row represents the adults, bottom row represents the children, and each column represents a different showing at the cinema, I can represent my data using this matrix. So it makes it a little bit easier for us to read. Spreadsheets are quite often using this methodology when they're doing calculations, recording data, processing data, etc. And it's something we can use mathematically, even on a page, that might help us make sure we get our heads around it and just record the data a little bit easier. Now, a thing to remember about 2 matrices is we can tell that they're equal to each other if they follow 2 properties. So first one being that they're of the same order, i.e. the same size. So if they're both 2 by 2, great. And all the corresponding entries are equal to one another. So let's imagine I've got a matrix 1, 2, 3, 4, and I was to tell you I've got another matrix which is 1, 2, 3, 4. Now if I was to call this matrix here and put my line down, they'd both be 2 by 2s, the entries would be corresponding so they're equal. However, if I was to add, let's say, a column 0, 0, now you might look at that and think, well, there's nothing in that column. One, what's the point of having it? Well, it's part of the data. We have to include it. We don't know what that column represents. So we have to include it if we're given it as part of the matrix. Then what this does is it changes the order. This one here has 2 rows and 2 columns, so it's 2 by 2. This one has 2 rows and 3 columns, so it's a 2 by 3. They are no longer equal to each other, despite the first part of it having the same entries. This extra column of zeros, because we can't ignore that it's now part of the matrix, means that our two matrices there, they're no longer equal to each other. Now this is important about matrices having the same order, because if two matrices have the same order, then they're compatible for addition and subtraction. And what we can do is, if we're adding two matrices, so let's say we're going to do this operation here, matrix A plus B equals C, what we do is we add the corresponding elements of each matrix. So we take Aij plus Bij equals Cij. So let's imagine I've got a matrix 1, 2, 3, 4. Let's go for that one. And I've then got a matrix 2, negative 1, 1, 0. And I'm adding them. So this represents my A and my B. To get this matrix C, what I do is I add each corresponding element. So I've got 1 plus 2. That's going to be my top left. So that's my 3. My 2 plus the negative 1. Well, that's 2 minus 1, which is 1. 3 plus 1, which is 4. And then 4 plus 0, which is 4 again. All I've done is added up each corresponding element. And that applies for subtraction. All we do is subtract each corresponding element. So looking again at this example here, what I'll do is I'll just take the exact same elements. So I've got my 1 there. I've got 2, 3, 4. This time though, I'm going to subtract the 2, negative 1, 1, 0. Now, one thing I want you to remember is this first matrix, take away the second one. Don't get the elements mixed up. So again, do it with the corresponding elements. This time I'd do 1, take away the 2, I'd get negative 1. I'd do 2, take away the negative 1, so minus minus becomes a plus, so that's 2 plus 1, which is 3. I've then got 3, take away 1, which gives me 2, and then 4, take away 0, which is 4. Don't get them mixed up and get the elements the wrong way around. You'll see why in just a second. But that is for subtraction. Addition and subtraction, fairly straightforward. And any matrix multiplied by a scalar, all we do is multiply each element of the matrix by the scalar. So again, same sort of logic, take each element on its own and just multiply it by that. So if I took this first matrix here, let's say the 1, 2, 3, 4, and I said I wanted to do 3 times it, I would just multiply every single element here by 3, and I'd have 3, 6, 9, 12. Straightforward enough. Treat each element on its own as we do the operations. Nice and easy. Now, we have to think about negative matrices as well, but the negative of a matrix G is denoted just simply by minus G. And what we can do is get this by negating each element of the matrix. So for example, if I told you I had a matrix H, which was given by negative G, all that would imply is that H of Ig, so every element in H, is just the negative of the corresponding element in G. It's essentially multiplying the matrix by a scalar of negative 1. It's that simple and straightforward. Negate everything, change the sign, job done. We can also take a matrix and switch the rows and columns. Now this is what's called taking the transpose of a matrix. So let's imagine, for example, I've got a matrix that's 1, 2, 3, and I had 0, 1, and 2. Let's imagine that was my matrix A, and imagine I wanted to take the transpose of A. Now just for a point of clarification, if I've got a matrix A, its transpose, denoted two ways, can be either the A dashed or the AT. I'm going to try and commonly stick with the AT in the work I'm going to do, but just be aware it could come up either way. All I do is I swap the rows and the columns about, and I'd end up with 1, 2, 3, 0, 1, 2. Now notice it's gone from a matrix where it's got 2 rows and 3 columns, so it's gone from a 2 by 3 to a 3 by 2. So note that not only does the elements in the matrix change, but the dimensions of the matrix change as well. They swap around. So be very, very careful with that. They can no longer be the same size if the matrix is like this. If it's a 3 by 3, it's going to stick to being a 3 by 3 when we take the transpose. But ones like this, where the number of rows and number of columns are not equal, that will be the case in the transpose. They'll just swap round. Now if we say that the transpose of A is equal to A itself, what that means is every element in Ij is equal to the corresponding element in Ji. What that means is the matrix is symmetric. Now this will be symmetric about what's called the leading diagonal. Now if we've got a matrix here, so let's say it's a 2 by 2, so let's say it's A, B, C and D, the leading diagonal is this one here. So a key point to note from this diagram I've given you here as well is it has to be an n by n matrix. Yeah, so the matrix has to have the same number of rows as it does column for it to be symmetric. And similarly, if the transpose of A is the negative of A, this means the matrix is what's called skew symmetric. And in this case, the matrix will have zeros in the leading diagonal. So this one here could look something like 0, A, B, and 0. Again, leading diagonal is that there. This time though, they're all zeros. So all we'd have is the negative of that. And these two elements would be the same, just opposite signs there. So that's what it means when it's talking about symmetric and skew symmetric. That's the only difference between them, is the signs in that leading diagonal. And it has to be the case of that for any n by n matrix to have a symmetric or a skew symmetric variant when we take the transpose. There's just a couple of other key points I want you to remember when we're working with matrix, and a couple of key characteristics we have to take into account. Firstly, we have what's called a zero matrix, denoted by O. Funnily enough, all entries of that are zero, as the name suggests. Now if we've got two matrices, A and B, and I do A plus B, and I get a zero matrix, what I can then tell you is that the matrix A is equal to the negative of B. So I can relate them to one another for that. Now we talked about commutative and associative laws earlier on in previous topics. Now when it comes to matrices, the commutative law holds for addition of matrices. So A plus B equals B plus A. But it does not hold for subtraction. So A minus B does not equal B minus A. That highlights one of the points I mentioned earlier about making sure you are doing the subtraction in the correct way round. We would not have gotten the answer we got earlier had we got the two matrices mixed up and done it the other way. So be careful. Commutative law does not hold for subtraction when it comes to matrices. The associative law holds for addition in this case. So your A plus B in a bracket plus C is the equivalent of A plus bracket B plus C. So just add them all together in whatever order you want. Again, it doesn't hold for subtraction. And it's the same with scalar multiplication. So it's distributive over addition. So K of bracket A plus B is the equivalent of KA plus KB. And there's a couple of elements that I want you to remember, a couple of key characteristics I want you to remember when looking at the transpose of matrices. So firstly, that the transpose of the transpose is the original matrix itself. If I do the matrix A plus the matrix B, as suggested in the second one given here, that's the equivalent of taking the transpose of A plus the transpose of B. So if you add them and then take the transpose, it's the same as doing each of the transposes, then adding it together. And then the final one, the final thing I want you to remember with matrices, is that K times A, and then you take the transpose of it, that's the equivalent of taking the scalar K and just multiplying the transpose of A by that scalar. Remember, the scalar is just a number. It has no effect itself on the matrix besides scaling each element up and down. So if we take that out as a factor, we'll get the same answer as if we had it in as a factor to begin with. Now these are all key things you have to remember when it comes to doing calculations with matrices and properties associated with them. We have to keep these in mind when we're working with the material, when we're working through the course, and when we're working through this entire topic of matrices. It's a good chunk of stuff and it's got a lot of applications we need to be able to do with them. But we have to know these properties, these characteristics off the top of our head to be able to recall and use them at the click of a switch.